All right, what's up, everybody? Time for some probability vocab in the basement. Let's do it. Here we go. So, just kind of want to look at some of the concepts and some of the terminology behind probability, right? So today in class, we started doing a bunch of math problems. We'll keep doing that when I see you again. But for now, right, so just kind of thinking about some of the language we're going to use, some of the big ideas behind this. You can soak in that sweet picture down here, right? So probability, right? We're essentially trying to think like, if we know what the whole group looks like, what do we got going on in our hand here? What are the chances, whatever. How likely is it we got some blacks or grays or whatever? In the second semester, kind of think the opposite direction. As we think about statistical inference, we're going to try to figure out if I have a sample of data in my hand, can I use that to figure out what's in the bucket? For now, right, we'll stay in probability world here, kind of thinking about this. So here's the deal. So first up, randomness, right? When we're talking about random events, like the flip of a coin or the spin of a roulette wheel, right? In the short term, I don't know what's going to happen, right? If I flip a coin one time, I can't tell you if it's going to be heads or tails. If we spin a roulette wheel one time, right, I can't tell you if it's going to land on red or black or green. Like I could tell you that there's about a 47% chance it lands on black, right? 18 out of 38 sections are black, or about a, 47% chance it lands on red, right? But like, that's it. In the short term, anything can happen. I could walk in, right, put a, $100 on my favorite number 6. I would never do that because I'd probably lose $100, right? But whatever, theoretically, I can walk in, put $100 on 6, win, boom, win a lot of money. Great. Who knows what would happen? But if we think about the long run, right, random outcomes are super structured in the long run. And when we say the long run, we're thinking theoretically an infinite number of trials. So although, right, if we're talking about a coin flip, just to kind of keep it simple, right, for a coin flip, although I can't tell you what's going to happen in one flip, or even necessarily two, we do have a pretty good idea about what would happen long term. For instance, if I flip a coin 1,000 times, I'm pretty confident I know I'm going to see around, right, not exactly, but around 500 heads and 500 tails. Right, so this is just the idea that short term, sure, anything can happen, but in the long term, right, there's a lot of structure. This is really what allows a casino to exist, right? So in a short term, first person walks in for the day at a casino, right? They could put all their money on their favorite number, right, and win the jackpot right off the bat. The casino's not worried about that. So sure, the first person they might have to give $100,000 to, whatever. But they're not really worried about it because they know in the long run, what happens with this roulette wheel is going to match their mathematical calculations, right? The kind of the probability theory. They know in the long run, people are going to lose more than they're going to win, right? And they're going to make money. And they can operate kind of basing their entire business on the long run, right? Because at a casino, right, it's not like roulette's getting played twice a day, right? You go to Foxwoods or Mohegan or whatever, roulette's getting played all day, every day by tons of people and tons of different roulette wheels and all that, right? There's thousands and thousands of spins of a roulette wheel every day at a casino. And so because they have those many, 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 many trials, right? Everything is happening in the long run. What actually happens on their casino floor starts to mirror what they expect to happen, mathematically speaking. Now we're just kind of jumping through a bunch of vocab. So when we think about an event, first up, right, sample space. So the sample space is the set of all possible outcomes for an event. So if we're talking about the spin of a roulette wheel and we bet on a color, right, so this is kind of our event. An event is a set of outcomes. So an event is the spin of a roulette wheel. If we're going to bet on color, the sample space, S, would be the set of all possible outcomes. So the colors could be black, could be red, could be green. So that's our sample space, right? Each of these is one particular outcome, right? Black is one possible outcome, red is one possible outcome, green is one possible outcomes. So like an event, right, it's kind of like a combination of outcomes, and a sample space, right, is a list of all possible outcomes for an event. Or here, right, if I talk about the roll of one die, here the sample space, right? What could happen if I roll one die? I could get a 1, 2, 3, 4, 5, or 6. And so if we were asked to define a sample space, we'd simply be listing all of the possible outcomes. And lastly, right, Pause the video. Think about it. Define the sample space. What would the sample space be for the sum of 2 days? And of course, right, you decided the sample space, you could get a 2, a 3, a 4, 5, 6, 7, 8, 9, 10, 11, 12, right? That's that. Sample space. This right here, we have what? Like 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 possible outcomes in this scenario. So that's the idea of the sample space. Right? We always want to consider that. And ultimately, the probability of kind of any outcome in the entire sample space is always going to be 1. This is getting a little ahead, right? But the probability that I get a 1, 2, 3, 4, 5, or a 6 when I roll a die is going to be 1, because I'm definitely going to get a 1, 2, 3, 4, 5, or 6. I guess unless it like stands on its corner, but you know what I mean. Probability. We keep talking about probability, so let's define that. So probability is the long-run relative frequency of an event. So the long-run relative frequency of an event. What does that mean? That means after many trials, relative to the total, how frequently did something happen, right? So like probability of heads, the long-run relative frequency, I could think if I flip a coin 1,000 times, right, of those 1,000 flips, probably wouldn't get exactly 500 heads, but we'll pretend this is the idea of long-run relative frequency. How many heads did we get out of how many total flips? As we mentioned, right, can't predict a particular outcome in the short term, but over time, right, we can make a lot of specific, or draw a lot of specific conclusions, because random outcomes are superstructured in the long run. Another way we might define probability is kind of the likeliness of an event, right? That's how we probably more commonly think about it. The chance that it snows, how likely it is that it snows on Friday or whatever, and so on. So this is maybe the more formal, like mathematical definition of probability. This is probably a bit more practical, right? This is probably what most of us are thinking about when we consider the value of a probability. And so on that note, probabilities are typically written as decimals. So it's like not wrong to use a percentage, right? But you're going to see in math books, they're typically written in their decimal form. And when they're written as a decimal, that means they're going to be between 0 and 1. Or if we consider them as percentages, right, that's going to be between 0% and 100%. So if something has a probability of 1 or 100%, that means it's definitely going to happen. It really bothers me when like they give a weather forecast. Like I was watching the weather today and it said there's a 100% chance of rain on Thursday. Like, how can you really say it's definitely going to rain on Thursday? Like, who knows what's going to happen tomorrow? Like, maybe you can tell me there's a 99.9% chance, but 100, I don't know. It makes me feel kind of uncomfortable. We don't really know until Thursday happens. But anyways, so probability of 1 means something is definitely going to occur, right? It is certain to happen. Whereas probability of 0, right, that's impossible. When I roll 1 die, the probability I get a number is 1. I'm definitely going to get a number. When I roll 1 die, the probability I get a 7 is 0. I'm definitely not going to get a 7 because there's only numbers 1 through 6 on the die. And of course, right in the middle here, right, that's like that 50% chance. That's kind of neutral, I suppose. Right, nothing groundbreaking here. I think we know this stuff. Closer to 1, something is more likely to occur. Closer to 0, something is less likely to occur. No big deal there. What else we got for vocab? So the law of large numbers. We saw this a little bit in the textbook. So here's the deal with the law of large numbers. The formal law of large numbers says the long-run relative frequency of repeated independent events settles down to the true probability as the number of trials increases. Another way we might say that is the experimental probability, what actually happens, gets closer and closer to the theoretical probability as the number of trials increases. So let's think about that with a coin flip. Here's what the law of large numbers is really saying. So the law of large numbers. We'll use coin flips because that's easy, right? The theoretical probability that we get heads, right? 1 side is heads out of 2 sides is 0.5. So what the law of large numbers is saying, let's say we flip a coin 10 times. If I flip a coin 10 times, the long run relative frequency would be, out of those 10 flips, how many actually come up heads. And so if we had more time, right, we don't with our crazy schedule this year, we would spend the class period flipping tons of coins. And then we would be able to see this rule kind of uncover itself. I could get exactly 5 heads, but like maybe not, right? Maybe I get 4 heads, or maybe I get 6 heads, right? So let's say I get 4. And so here, the probability, the long run relative frequency is 0.4. That's like kind of far away from that, right? That's 10% off. Now, let's say I flip a coin 100 times. So the long run relative frequency would be, of those 100 flips, how many of those actual flips were heads? And again, right, like we expect it to be about 50-50, but like that probably wouldn't happen. And again, ideally, we'd be flipping coins 100 times right now to see what happens. Maybe you get, I don't know, 46 heads. Like here, you're only off by 1 from what you would expect 5. Here, you're off by 4 from what you would expect 50. But this overall proportion, right, this is closer to 0.5. And that's what the law of large numbers is saying. The law of large numbers is saying the more I do something, the more I flip the coin, the closer this actual fraction, what actually happened, this experimental probability, the closer this is going to get to this theoretical probability of 0.5. Right? So if you said like, oh, I flipped 100 coins and like it's not 50-50 yet, what's going on? I would just be like, you didn't flip enough. Long run, right? That's theoretically an infinite number of trials. And then, right, so then if we flip a coin, I don't know, 10,000 times, maybe of those 10,000 flips, maybe, I don't know, 5,000, whatever, 99 of them were heads. That's like 99 away from what we would expect, right? This is only 4 away from what we'd expect 50. This is only 1 away from what we'd expect 5. This is 99 away from what we'd expect 5,000, but at the same time, right, this comes out to be 0.5099. And that is the closest of these 3 made-up examples, black, green, and blue here. But that's even closer to this 0.5. And if you were like, I flipped a coin 10,000 times and I still didn't get exactly 50% heads, you know what I'd say. Keep flipping. Eventually, the more and more we flip this coin, the closer and closer what actually happens, that experimental probability gets to what we expect mathematically, this theoretical probability. So that's what the law of large numbers is telling us. For real life to match the mathematical theory, we need lots and lots and lots of trials. That's why a casino can function, based on all these mathematical rules, because they have many, many, many trials. That's actually why I think that's why we started to see statistics infiltrate baseball before the other sports, because in baseball there's 162 games, right? And there are many, many, many trials. Maybe a guy bats 4 or 5 times a game, right? So you got lots and lots of trials. So then you can start to apply some of these probability and statistical ideas, whereas that's a little harder maybe in football when there's 16 games. Although statistics is taking over all sports. Analytics, I'm sure you've heard. Anyways, what am I babbling about? What do we got next? Equally likely. I mean, this is like the easiest word ever. Equally. Equal means the same. Likeliness of an event. That's the probability. Same probability. Done. Right? Equally likely, or it means events have the same probability to occur. Some events are equally likely, some aren't. If I'm talking about spinning the spinner, any of these numbers are equally likely to occur because the sections are all the same size. But like numbers less than 10, these ones would be more likely than numbers greater than 10. Or if I think about our old friend here, the roulette wheel, right? Like getting red, why is that green? That's right, 18 out of 38. That's equally likely as the spinner landing on black, which is also 18 out of 38. But getting red is not equally likely as the spinner landing on green, right, which is 2 out of 38. So, right, equally likely just means that they have the same probability to occur. No big deal. So, here's a little story time for you about how this was used. So once upon a time, there was a bunch of grad students who went to Reno and they played Keno. So Keno's like a game. It's at restaurants now in Connecticut all over the place. Maybe you've seen it, right? There's like a big board of numbers here. There's 1 through 80. You get like a sheet. You pick a bunch of numbers. Your numbers come up, you win. So it's like kind of bingo-ish, I guess. So what these people did is they went to Reno, Nevada, I think, and they played Keno a ton. So they played Keno like whatever, all day. And as they did that, they recorded what was happening. So they recorded tons and tons and tons of data. Now they knew in the long run, all of these numbers should be equally likely to occur. right? We should, if we play Keno and record thousands and thousands and thousands of data points, each of the numbers 1 through 80 should come up about the same time. However, what they noticed is that that's not what was happening. Some of the numbers were coming up more often than others, right? And this is where the psychology comes into play, and also the game is rigged, right? Maybe they're having numbers come up more often that people don't bet on because, right, like no one wants to give away money, everyone wants to take it. So what happened was these grad students noticed that some numbers were more likely than others to occur. They knew that was messed up. They knew they should all be equally likely. So they realized the game had to be fixed in some way. They went back. They knew some numbers were more likely to happen because the game was rigged. They bet on those numbers that were more likely to happen, and they ended up winning $50,000. I mean, that sounds kind of simple, right? It's not that easy. Otherwise, we'd all be out winning $50,000. Right? Just a little application of equally likely events, or the definition of it. So vocab-wise, that's it. Next video up, we'll talk about independent disjoint events. See you there. Wait, I'm still here. See you there.